may not realize it, but we're surrounded by arguably the greatest, most revolutionary invention of the last 50 years. It's in TVs, stereos, watches, cars, phones, traffic lights, and pretty much every appliance in your kitchen. In fact, these days, if a device uses electricity, it probably uses one. The tiny gizmo in question is, of course, the silicon chip. Making these extraordinary miniature electronic brains is one of the most complex manufacturing tasks ever attempted. So, how do they do it? Texas, USA. Home to big stuff. Big cows, big boots, big hats, big mustaches. But Texas is also the birthplace of a miniaturized miracle, the silicon chip. And here in Sherman, 20 miles north of Dallas, is the MEMC fabrication facility. In this strange, futuristic-looking plant, they produce silicon wafers, which are the basis for all modern microchips. Silicon has special properties because it's what's called a semiconductor. That means that depending on how it's treated, silicon can either conduct or block the flow of electricity. It's this property that makes it ideal for supporting the millions of tiny transistors necessary for a modern computer chip. But because these transistors are so incredibly small, the silicon base on which they rest needs to be absolutely flawless. It took decades to perfect the process of producing silicon with a perfect monocrystalline structure. They begin with raw polysilicon, or poly, and heat it to over 2,500 degrees Fahrenheit inside a special sealed furnace, which has been purged with argon gas to eliminate any air. The resulting lake of molten silicon is then spun in a crucible, and a silicon seed crystal, roughly the size and shape of a pencil, is lowered into it while spinning in the opposite direction. As the molten polysilicon is allowed to cool, the seed crystal is slowly withdrawn at around 1.5 millimeters a minute. The result is a single silicon crystal weighing around 440 pounds and with a diameter of around 200 millimeters. The crystal is so strong its entire weight can be supported by a single thread just 3 millimeters across. But it is brittle, and it must now be cut down to size without shattering. After testing with chemicals and X-rays to check its purity and molecular orientation, it's fed to a silicon salami slicer. This 10-ton wire saw uses a fast-moving web of ultra-thin wire to produce wafers of silicon that are just 2/3 of a millimeter thick and 99.999% pure. Once cut, there are microscopic marks left on the wafer surface, so it's time for a buffing using a process called lapping. After a twirl in this high-powered polisher, they are still not smooth enough. So they're given yet another buff using a chemical process. The result is wafers of silicon with a surface roughness of less than 1/1,000,000th of a millimeter. Buffed to a sheen, they're finally ready for etching with the circuit design. Coming up, how do they eliminate the biggest enemy of manufacturing in a microscopic environment, the common dust particle? Find out next on How Do They Do It? Packing millions of transistors onto these tiny silicon wafers is the job of chip manufacturers like Texas Instruments. Back in 1958, the inventor of the integrated circuit, Jack Kilby, managed to squeeze a single transistor onto his design. These days, the latest generation uses almost 1 billion, And according to Moore's law, that number doubles every 2 years. Of course, the more they try and pack into the design, the smaller each transistor needs to get.
There are over 250 million transistors in this design. Someone has to shrink them down to this.
Working at this microscopic scale exposes the chip makers to a major problem. When a transistor is only 1/10,000th of a millimeter across, the smallest particle of dust is enough to cause an electronic train wreck. So before staff members like Dane Bailey set to work in the fab, it's on with the bunny suit.
For our general product that we make here, a DSP, typically takes on the order of about 1,500 individual processing steps from start to finish.
With an area of just under 194,000 square feet, the fab is a Class 1 clean room. Thanks to 12,000 tons of air conditioning equipment, the air is 1,000 times cleaner than a hospital operating room.
There's actually less than 100 particles per cubic foot of air. As few as one particle landing on a critical area can kill a chip.
To give you an idea how clean this room is, walking alone produces 5 million particles every minute. So to avoid contamination from the inadvertently dusty staff, front opening unified pods, or FOUPs, transport packets of wafers through the intricate process of component construction. The key problem is miniaturizing the complex designs and imprinting them onto the wafers. It's done through a process known as photolithography. First, the wafer is coated with photosensitive chemicals which harden when exposed to UV light. In sealed darkrooms, light is shown through an image of the design, then through a miniaturizing lens and onto the coated wafer. When the chemical is washed off, the design remains, just like a developed photographic image. But in order to pack all the components onto the wafer, they are built up layer by layer, like floors in a miniature skyscraper. To complete the job, the FOUPs cycle the wafers up to 40 times, repeating the photo etching process for each new layer. Some layers are cooked, some blasted with ionized plasma, some bathed in metals. Each different type of treatment changes the properties for that layer and slowly forms part of the jigsaw making up the chip's design. The finished sheets of silicon wafer carry up to 1,000 individual microchips and billions of circuit elements. All that remains is to slice and dice, and the journey from sand to circuit board is complete. What was once a worthless pile of sand can now change hands for more than nearly $700 an ounce and calculate pi to 1,000 decimal places in the blink of an eye. Metaphysical poet William Blake reckoned he could see the world in a grain of sand. But if he were to look again today, he would surely be more amazed to discover a billion tiny transistors.